At 200 meters down, sunlight vanishes forever and pressure mounts. Every 10 meters adds another atmosphere, crushing life as we know it. This is where the creatures of the deep grow shockingly creepier, evolving molecular defenses so their bodies do not collapse, and beginning a transformation the surface world can barely imagine. What forces twist evolution so far? The giant jaws, glassy eyes, and bodies lit from within become the only way to survive. The journey into the abyss starts here. At roughly 200 meters below the surface, the last rays of sunlight fade and vanish. Above this depth, in the epipelagic zone, familiar blue water still glows with daylight. But here, at this invisible boundary, the ocean changes. Sunlight no longer reaches below. The water transforms from clear blue to a deep, endless black. For marine life, this is not just a color shift. It is a total change in the rules of survival. The final reach of the sun is gone. The epipelagic zone stretches from the surface down to 200 meters. It is the only part of the ocean where sunlight is strong enough for photosynthesis. Most of the world's fish, plankton, and all surface-dwelling predators live here. But at 200 meters, the light drops off sharply. Even in the clearest tropical seas, less than 1% of surface sunlight remains. Below this line lies the mesopelagic, the Twilight zone, running from 200 to 1,000 meters. Here, the world is cloaked in permanent dusk. The blue fades, replaced by a dim haze that grows darker with every meter. Twilight becomes the rule. This boundary is not just a number on a depth chart. It is a hard limit for vision, for plant life, and for the way creatures sense and hunt. The disappearance of light at 200 meters divides the ocean into two worlds, one where sight rules and another where darkness reigns. Above, colors still exist. Below, everything becomes shadow and suggestion. The pressure is already building, but it is the loss of light that triggers the first great transformation. Fish that cross this threshold leave behind the familiar and enter a realm where the senses must adapt or fail. In the Twilight zone, vision becomes a game of survival. Eyes grow larger, tuned to catch the faintest glimmer from above. Some animals develop mirror-like structures in their eyes, reflecting every stray photon back for a second chance at seeing. Others begin to lose pigmentation, their bodies turning silver or even transparent to blend into the dimness. The deeper they go, the more they must change. Vision is repurposed into extreme sensitivity. The ocean's light curve drops off with a steepness that is hard to imagine. At 100 meters, about 20% of sunlight remains. At 100 to 50 meters, it is just a few percent. By 200 meters, the world is almost completely dark. This is the edge, the final reach of the sun. Beyond this, creatures face a new world shaped by darkness, crushing pressure, and the constant threat of the unknown. The map of the deep begins here, at a boundary that is both a physical fact and a line that life must cross to become something else. Darkness does not simply erase sight, it reshapes behavior, anatomy, and chemistry. The first rules of deep-sea life are written at 200 meters, where sunlight ends and the deep begins. Every 10 meters deeper, the ocean gains another atmosphere of weight. Dive to 1,000 meters, and the water above presses with more than 100 times the force felt at sea level. This is not an abstract statistic. This is a constant, invisible pressure that shapes every living thing it touches. For a single cell, that pressure is a crushing reality. It can twist molecules, collapse any gas-filled spaces, and force water into places it does not belong. Bones and swim bladders that work near the surface become liabilities. Rigid structures risk shattering or imploding. Soft, flexible bodies fare better, but softness alone is not enough. Surviving the deep means rethinking life from the inside out and adapting at a level we cannot see with the naked eye. The real battle is molecular. High pressure can pry apart the proteins that run a cell, causing them to unfold and lose their function. To stand up to that squeeze, deep-sea animals build a kind of chemical armor. One of the most important shields is a molecule called trimethylamine N-oxide, known as TMAO. TMAO acts like a brace for proteins, helping lock them into shape and resisting the distorting effects of pressure. As depth increases, so does the concentration of TMAO inside cells. This is not a small tweak. Without enough TMAO, proteins would unravel and the machinery of life would grind to a halt. Scientists have measured TMAO levels rising almost in direct proportion to depth, forming a molecular ladder that matches the climb in pressure. Chemistry does not stop with proteins. Cell membranes face their own threat. Under extreme pressure, many fats stiffen and threaten to freeze cellular machinery in place. Deep-sea animals solve this by loading their membranes with unsaturated fatty acids, oily molecules that stay fluid even in near-freezing water and under enormous pressure. That fluidity keeps membranes flexible and functional, allowing nutrients, signals, and waste to move in and out of cells. Many species also use small stabilizing molecules called piezolites, which further support proteins and membranes against the relentless squeeze. These chemical adaptations write the rules for how deep life can go. There may be a hard limit, a depth where even TMAO and piezolites can no longer hold proteins and membranes together. That limit appears to sit near the deepest trenches scientists have sampled, where only a handful of specially adapted species persist. From the smallest microbe to the largest fish, every deep-sea creature is sculpted by these invisible forces. The deeper the descent, the more radical the chemistry becomes. Evolution responds by reshaping bodies and behaviors that seem almost impossible by surface standards. In the deep ocean, survival is not just a matter of form. It is a matter of molecular engineering, written into every cell. Below the sunlit world, vision faces a new challenge. As sunlight fades, eyes must adapt to an environment where every photon is precious. Many deep-sea fish develop eyes that seem impossibly large for their bodies. The hatchetfish, for example, has eyes that dominate its head, angled upward to catch the last hints of blue filtering down from above. These eyes are not just big, they are built with oversized lenses and layers of rod cells tuned to detect the faintest glimmer in the twilight. In some species, mirrors inside the eye reflect stray light back through the retina, doubling the chance of picking up a signal. But size is only part of the strategy. Color fades quickly at depth, and pigment becomes a liability. To avoid casting a shadow or giving themselves away, many fish lose much of their skin color. Some become silver, scattering what little light remains. Others take the transformation further, turning nearly transparent. Lanternfish and glass squid are so clear that their muscles, nerves, and even internal organs can be seen through their skin. Only their eyes and guts remain visible, parts that cannot be made see-through without losing their function. Transparency is more than camouflage. It is a way to vanish in a world with nowhere to hide. With little pigment to block light, these creatures blend into the dim haze. The trade-off is delicate. Eyes must be large and sensitive, but not so obvious that they betray the animal's presence. Every adaptation is a balance between seeing and being seen, shaped by the relentless math of light and shadow in the deep. Every night, as the sun dips below the horizon, a hidden migration begins in the deep. Billions of creatures, mostly lanternfish, rise from the darkness of the twilight zone toward the surface. This nightly journey, called Diel vertical migration, is the largest animal movement on Earth by sheer mass. From depths of 600 meters or more, lanternfish and their neighbors ascend hundreds of meters under cover of darkness, searching for plankton in the upper layers where food is most abundant. At dawn, they retreat back to the safety of the deep, evading predators that hunt by sight. This vertical commute is not a small event. It involves more biomass than all the world's herds of wildebeest, caribou, and elephants combined. The scale is hard to imagine. Sonar scans reveal a living layer that shifts up and down in the water column like a ghostly tide, thick enough to baffle early oceanographers who mistook it for the seafloor itself. Lanternfish, with their glowing photophores, make up the backbone of this migration. There are over 250 species, and together they outnumber nearly every other group of vertebrates in the ocean. Their nightly rise and fall is more than a feeding strategy. It is the engine of the ocean's biological pump. As these fish eat near the surface and release waste at depth, they shuttle carbon from the atmosphere into the deep sea, helping to regulate the planet's climate. This migration shapes the entire ecosystem of the Twilight Zone. It drives the need for light-based camouflage, for eyes tuned to faint glimmers, for bodies built to move between worlds. In the darkness below, the nightly parade of lanternfish is both a feast and a challenge, fueling predators and shaping the evolution of every creature that crosses their path. In the ocean's perpetual dusk, light has a new meaning. When the last rays of the sun fade, survival depends on more than hiding in shadow. Life invents its own illumination, and that invention changes everything. The chemistry behind bioluminescence is simple and astonishingly efficient. A molecule called luciferin reacts with oxygen. A special enzyme called luciferase acts as the spark, setting off a reaction that releases energy as visible light. The process produces almost no heat, so nearly all the energy becomes light. In a world where every calorie counts, that efficiency matters. Some animals synthesize their own luciferin and luciferase. Lanternfish and hatchetfish make their own light internally. Others host glowing bacteria inside specialized organs. Anglerfish, for example, carry living lights at the tip of a modified fin spine. No matter the source, the effect is the same, a flash or a steady glow that can be switched on or off at will. That variety of solutions is one of the deep sea's signature features. Control is the real power. Creatures trigger light in precise patterns. Sometimes they burst a signal, sometimes they produce a steady beam. Colors are selected for purpose, most often blue or green, and in rare cases red. Each wavelength is tuned to the animal's needs and to the darkness that surrounds it. This precise control becomes a language. Light is a tool for many jobs. It is used for communication, to find or attract mates. It is used for attraction, to lure curious prey within reach. It is used for camouflage, countering the faint downwelling glow so an animal can vanish when viewed from below. It is used for hunting, to reveal silhouettes or to startle and confuse. For example, hatchetfish use ventral lights to erase their silhouette, while anglerfish dangle a glowing lure to bring food close. Because the reaction gives off almost no heat, bioluminescence is an economical way to use scarce energy. Cold light conserves calories, and that conservation shapes behavior and design. Small organs, precise control, and timing all reflect the need to get the most from every molecule. Energy economy drives form and function. In the Twilight Zone, inventing light rewrites the rules of existence. Predators learn to hide their intent, prey learn to flash warnings and decoys, and whole ecosystems become organized around light. The transformations you see in these dim waters are not tricks. They are survival strategies honed by pressure, darkness, and limitless time. Here, in the dim between surface and abyss, life lights the way. Lanternfish and hatchetfish have mastered the art of vanishing in plain sight. In the perpetual dusk of the Twilight Zone, predators search for shadows against the faint glow from above. To escape detection, these fish evolved a remarkable trick: Counter-Illumination. Along their bellies, rows of tiny organs called photophores emit a controlled glow. This light is deliberate. Each species carries its own pattern, and the brightness is tuned with astonishing precision to match the color and intensity of the dim sunlight that filters down from the surface. Spectral tuning makes the light nearly identical to the blue hue of the ocean overhead. For a predator lurking below, the silhouette of a lanternfish or a hatchetfish simply disappears. Their bodies blend seamlessly into the background, as if erased by their own biological spotlight. Hatchetfish, push this adaptation further. Their slim, reflective bodies are shaped like the blade of a hatchet, and their ventral photophores form a line that matches the band of light above. These fish can adjust the intensity of their light in real time, responding to changes in the ambient glow as clouds pass or as they move up and down through the water column. Lanternfish, with more than 250 species, display an incredible variety of photophore arrangements. Some show lines, others clusters, each a living barcode. These patterns serve camouflage, and they also help individuals recognize members of their own species in the darkness. Counter-Illumination is not a passive trick. It is an active, energy-intensive process, finely calibrated by evolution. In the shifting blue-black world of the Twilight Zone, survival depends on matching the light above, photon for photon, wavelength for wavelength. For lanternfish and hatchetfish, the difference between being seen and being invisible is measured in the faintest trace of light. In the deep ocean, darkness is more than a backdrop. It is a resource, and some predators have learned to weaponize it. The anglerfish stands out, not just for its grotesque silhouette, but for the glowing lure that dangles from its head. This lure, powered by bioluminescent bacteria, serves a double purpose. It draws in prey, and in a world where encounters are rare, it also acts as a beacon for potential mates. For anglerfish, the challenge of reproduction has led to a solution as strange as the environment itself. Males are born small, with little function beyond finding a female. When he succeeds, the male bites into her skin and fuses for life. His body dissolves into hers, organs shrinking, bloodstreams merging, until he is reduced to little more than a pair of gonads, permanently attached and feeding off her blood. Some females carry several fused males at once, each a living remnant of a chance meeting. This is sexual parasitism, an evolutionary answer to the near impossibility of finding a mate in the abyss. Predators here do not just rely on lures. Dragonfish, long and needle-toothed, have evolved a way to hunt in near invisibility. Most deep-sea creatures see only blue-green light, but dragonfish produce and detect far-red bioluminescence, light at wavelengths around 700 nanometers. This private spectrum is invisible to most eyes in the ocean. A special organ beneath the dragonfish's eye emits this hidden light, creating a searchlight only it can see. To other animals, the dragonfish is a shadow. To the dragonfish, the darkness is alive with unseeing prey, outlined by a secret glow. The idea of a private beam of light changes everything about who can hunt and who can hide. These adaptations are the products of relentless evolutionary pressure. In the deep, where solitude and hunger rule, survival demands radical solutions. Anglerfish fuse for life, and dragonfish hunt with invisible beams. Each is locked in an arms race, pushing the boundaries of what is possible in the dark. Fangtooth and Viperfish are the deep's mechanical hunters, shaped by scarcity into living traps. The Fangtooth, an Oplogaster cornuta, carries teeth so enormous they cannot fit inside its own mouth. Some of these fangs are longer than the fish's own head, pointing straight up even when the jaws are closed. This is not a mistake of nature. It is a calculated design. In a world where meals are rare and unpredictable, every encounter matters. A prey fish that brushes too close has almost no chance. The Fangtooth's jaws snap shut with force, those oversized teeth locking its victim in place. There is no need for speed or precision. The goal is simple: grab, hold, and never let go. Losing a meal could mean weeks of hunger. The Viperfish, Chauliodus sloani, takes the ambush strategy to another level. Its lower jaw is hinged and lined with fangs so long they curve outside the mouth. These jaws can open wide, creating a gaping maw ready to impale anything that drifts near. Along its body, the Viperfish sports a series of photophores, tiny light organs that can flash or pulse. These lights are not just for show. They serve as lures, drawing in smaller fish and shrimp or confusing predators in the darkness. When the moment comes, the Viperfish lunges with a burst of speed, using its needle-like teeth to spear prey before it even knows what happened. Both hunters rely on patience and surprise. They drift, nearly motionless, conserving energy in the cold, high-pressure dark. Their jaws and teeth are not just weapons, they are insurance against the deep's relentless scarcity. When prey is finally within reach, there is no second chance. Mechanical extremes, oversized fangs, unhinged jaws, and luminous lures are the tools that let these predators survive, where failure means starvation. In the deep, evolution rewards the grotesque, turning every meal into a matter of life and death. In the deep sea, where even the most fearsome jaws can miss their mark, the Gulper eel has taken a different approach. Its silhouette is unmistakable. A slender, whip-like tail and a head dominated by a mouth that can open wider than its own body. Unlike the Viperfish or Fangtooth, the Gulper eel does not rely on oversized teeth or speed. Instead, it waits in the darkness, drifting with its enormous mouth agape. When prey wanders close, sometimes a fish, sometimes a swarm of shrimp, the eel snaps its jaws shut, swallowing nearly anything that fits. This is not a matter of precision. The Gulper eel's jaw is hinged and its skin is loose, allowing both mouth and stomach to balloon outward. It can engulf animals as large as itself in a single bite. The anatomy behind this feat is as strange as it is effective. The Gulper eel's lower jaw is attached to the skull by an elastic ligament, letting it swing open almost like a trap door. Its stomach is equally distensible, stretching to accommodate massive meals. This strategy is a response to the economics of life in the deep. Food is rare, and the energy cost of hunting is high. The Gulper eel has adapted by maximizing its chances in every encounter. When opportunity comes, it consumes as much as possible, then digests slowly over days or weeks. The rest of the time, it barely moves, conserving energy in the cold, high-pressure dark. Unlike surface predators that chase and corner their prey, the Gulper eel's method turns scarcity into opportunity. It is not built for speed or strength, but for patience and sudden abundance. One meal can sustain it for weeks. This is the final marvel of deep-sea predation, jaws and stomachs that rewrite the rules of what a fish can eat, all in service of survival where failure is not an option. After this, the story of deep-sea hunting shifts again, from brute force and sudden strikes to the silent, ghostly strategies of creatures built for stealth and invisibility. Far below the hunting grounds of Fangtooth and Viperfish, a different kind of life drifts in absolute silence. Here, jellyfish and siphonophores glide through the water, their bodies almost entirely made of water and collagen. These creatures are not built for speed or violence. Instead, they embody a strategy of extreme energy conservation. With bodies that are up to 95% water, they achieve nearly perfect neutral buoyancy. That means they neither sink nor float, and they need almost no energy to hold their place in the water column. The physics is simple and powerful. By matching the density of seawater, they can drift for days or weeks, spending only the bare minimum of energy on movement. Jellyfish pulse gently, their slow contractions barely disturbing the water. Siphonophores, some stretching dozens of meters long, assemble colonies that move as a single, ghostly organism. Their tissues are so thin and clear that they seem to vanish into the darkness, offering little for predators to see or bite. Muscles are reduced to wisps, skeletons are absent. The metabolic demands here are among the lowest in the animal kingdom. In a world where food is rare and hunting is costly, these gelatinous drifters have traded strength and speed for invisibility and patience. This strategy comes with trade-offs. Gelatinous bodies are fragile, easily torn by currents or the jaws of a passing predator. But in the deep, where the water is calm and encounters are rare, the advantages are clear. Energy saved is survival gained. Their ghostly forms hint at a world where the rules of life are written not by power, but by the quiet logic of drifting, conserving, and waiting for the next faint trace of food. Some creatures of the deep have taken invisibility to the next level, not by becoming transparent, but by erasing nearly all light that touches them. In the perpetual night of the midnight zone, certain fish and sharks have evolved skin so black it absorbs more than 99% of incoming light. This is not just dark coloration. Under a microscope, their skin is packed with melanosomes, tiny rod-shaped organelles filled with melanin, arranged in dense, chaotic layers. When a stray photon strikes the surface, it ricochets through this maze, scattering again and again, until almost nothing escapes. Reflectance drops below 0.5%, rivaling or even surpassing the darkest engineered materials ever made. For predators and prey alike, this adaptation is a shield. Bioluminescent flashes from hunting rivals or searching eyes vanish against ultra-black skin. The outline of a dragonfish or a deep-sea shark becomes a void, impossible to pick out even when illuminated by another animal's light. In some species, the only visible features are the glowing photophores, light organs that stand out against the blackest backdrop nature can build. This camouflage works in every direction, not just from above or below. It is a solution forged by relentless selection, where even a faint glimmer could mean detection and death. Ultra-black skin has evolved independently in multiple deep-sea lineages. The same basic architecture appears in dragonfish, anglerfish, and several deep-sea sharks. Each uses melanosome-packed tissue to trap light, but the details differ. Some arrange their melanosomes in tight, ordered stacks, others in tangled mats. The result is the same: near-perfect absorption, invisibility in a world where light is both weapon and warning. This is the endpoint of camouflage, where darkness itself becomes armor. At depths where the water weighs as much as a small car, pressing on every square inch, the Dumbo octopus drifts with a quiet grace. Unlike its shallow water cousins, this cephalopod has traded the jet bursts that define most octopus movement. Instead, it relies on a pair of soft ear-like fins that undulate gently along its head. These fins provide slow, steady propulsion, more gliding than swimming, allowing the animal to hover just above the seafloor with barely a ripple. Each movement is measured, conserving energy in a world where calories are precious and food can be weeks apart. The Dumbo octopus has shed many of the defenses that its relatives depend on. There is no ink sac to release a smokescreen. In the darkness of the abyss, ink serves no purpose. The skin is thin and gelatinous, almost translucent, offering little resistance to the crushing weight of the deep. Chromatophores, the pigment cells that let other octopuses change color in a flash, are reduced or absent. Camouflage here is not about color, but about blending into the slow, drifting stillness of the water itself. Energy economy rules every aspect of the Dumbo octopus's design. Muscles are soft, arms are delicate, and the body is filled with water rather than dense tissue. This reduces the cost of movement and helps the animal maintain neutral buoyancy, floating effortlessly at depths of 4,000 meters or more. Even feeding is gentle. The Dumbo octopus hovers above the mud, using its arms to funnel small crustaceans and worms toward its mouth. Every adaptation is tuned for survival in a place where the margin for error is razor thin. In the deep, the familiar octopus is reimagined, redesigned not for speed or escape, but for endurance, patience, and the quiet mastery of the abyss. Giant isopods the size of footballs, amphipods as long as a human hand, and sea spiders that dwarf their shallow cousins. These are some of the ocean's most unexpected giants. Deep-sea gigantism remains a puzzle. Scientists have proposed several explanations, but none stands alone. One idea points to cold, deep waters that slow metabolism. In these frigid depths, chemical reactions crawl, and animals can afford to grow slowly, reaching sizes impossible in warmer, faster-paced shallows. Another hypothesis centers on oxygen. Colder water holds more dissolved oxygen, and some researchers suggest this abundance allows larger bodies to function efficiently, even with sluggish metabolisms. Food scarcity plays its part as well. Down here, meals often arrive in sudden, massive pulses, such as a whale fall, a large carcass, or a rare plankton bloom. Bigger bodies can store energy for long stretches between feasts, outlasting smaller competitors during lean times. There is also less predation pressure. With fewer hunters, there is less need to stay small and nimble. Each of these ideas fits part of the pattern, but the full answer remains elusive. Gigantism in the deep is not universal, but where it appears it hints at a complex balance of temperature, oxygen, food, and evolutionary opportunity, an ongoing mystery waiting in the darkness. The deep sea holds a gallery of giants that seem to defy everything we know about life in the ocean. The giant isopod, Bathynomus giganteus, can reach more than 40 centimeters in length, about the size of a football. Its armored shell and many-legged body look like something out of prehistory, but this is a living crustacean related to the tiny pill bugs found in gardens. In the cold, high-pressure darkness, giant isopods roam the seafloor, scavenging for anything edible: fish carcasses, squid, even the remains of whales. Their size is a direct response to the deep, slow metabolism, long lifespans, and the need to store energy between rare, unpredictable meals. Amphipods in the deep ocean take gigantism even further. While their shallow water cousins are barely visible, some deep-sea amphipods stretch as long as a human hand. These shrimp-like scavengers gather in swarms around fallen carcasses, their large bodies giving them an edge in the race for food. The abundance of dissolved oxygen in the cold water, combined with low temperatures, may allow these creatures to grow at a pace impossible in warmer, shallower seas. Sea spiders, or pycnogonids, add another layer of strangeness. Deep-sea species can have leg spans more than half a meter across, dwarfing the spindly forms found in tide pools. Their bodies are reduced to little more than a central hub, with organs stretching into their long, thin legs. Each of these giants is a reminder that, in the abyss, familiar rules break down. Size becomes a survival tool, shaped by the slow rhythms, sparse food, and vast emptiness of the deep. Right now, over 80% of our ocean remains unexplored, a blue-black realm where creatures stranger than fiction thrive in total darkness and under crushing pressure. Each year, scientists discover new species emerging from the abyss, organisms that push the boundaries of what we think life can be, and that reshape our understanding of evolution and adaptation. As deep-sea mining and climate change threaten these hidden worlds, what is at stake is not just mystery, but the blueprint for survival itself. The deep ocean's secrets may yet decide our own future, by teaching us how life endures in extremes, and by holding clues to medicines, ecosystems, and resilience we have not yet imagined. If this film stirred your curiosity, share your thoughts in the comments below.